Okay, perfect. Okay, welcome everyone to another MCRN Colloquium. Today we're lucky to have Professor Jason Mireles-James. Did I say that right?
Perfect.
Okay, great. From Florida Atlantic University. He got his PhD in mathematics at the University of Texas, Austin in 2009. He has research interests in computational topology and dynamical systems, a posteriori analysis and numerics in dynamical systems, and KAM theory, which is on the existence of numerical approximation of invariant manifolds. And today he'll talk, I think, a little bit maybe about that, if I'm not wrong, introduction to the parameterization method for invariant manifolds. And yeah, with that, please take it away.
Okay, thanks a lot for the wonderful introduction. Yeah, so when I was invited to speak at this session, I wasn't sure what to talk about because I don't, I wouldn't consider anything I do directly climate science, but I do a lot of work in computational dynamics and computing invariant manifolds and things like that. And I thought I might take the opportunity to just give a little bit of an introduction to what's called the parameterization method, or what some people call the parameterization method, which is just a computational approach, a computational and analytical approach to studying invariant manifolds. And my hope is that, I'd like to give a talk would be understandable, maybe even on an advanced undergraduate level, kind of introducing this topic. And then if anyone gets excited about it, we could talk more offline or at the next conference we bump into each other at, or whatever. Okay, so that's my goal. So let me start with sort of the trailer to the movie, which is so what is the parameterization method then? So I mentioned invariant manifolds. Basically, the parameterization methods is a collection of tools, all closely related, for studying, say, recurrent invariant sets that happen to be smooth manifolds. And beyond that, their local stability, and then maybe even their attached stable and unstable manifolds. So the idea behind the parameterization method is that these objects of interest, they often solve some invariance equation. And once you write down this invariance equation, you can kind of change gears and think of it as some functional equation for the unknown parameterization. And now you can you have available all of your tools for studying functional equations, all of your analytic and numerical tools for solving these kinds of equations. And now, parts of the parameterization method, or what some people now have been calling the parameterization method, a lot of these ideas go back much further than the early 2000s, even back to the work of Poincaré and Lyapunov. So, why call this a method, or why give it a name at all? And I think a collection of ideas starts to become a method when, you have many different problems that you can kind of bring under the same umbrella, and you start to have existence and uniqueness theory for these different classes of problems, different good numerical algorithms that sort of cover lots of different problems, a posteriori theory and things like this, so that when a collection of methods stops being a bunch of isolated islands and kind of congeals together into a more like a continent, then maybe the word method starts to be appropriate. And the term parameterization method comes from maybe half a dozen papers in the early 2000s. Three of them, these papers by Cabré, Fontique, and De la Llave. These parameterization method for invariant manifolds, parts 1, 2, and 3, which really dealt with invariant manifolds attached to fixed points of maps. But the maps could be maps on Banach spaces. So this was a pretty general formulation already. And then 3 more papers by Alex Haro and Rafael De la Llave on invariant circles and their attached invariant manifolds. And again, you started to see with these 6 papers a common approach being applied to all of these problems. Now, since then, this is 20 some years ago, this parameterization method has been expanded to cover many different kinds of problems about invariant sets. So problems for diffeomorphisms, invariant manifolds for ODEs, delay differential equations, all kinds of PDEs, all kinds of integral equations, So, you know, has really grown into many different areas in dynamical systems. Even by now, there's a very nice book by Alex Haro and a number of his collaborators from Barcelona. You know, this is a really like a research monograph on this parameterization method. And if you look at the bibliography, there are hundreds of citations. So, and this was already back in this was state of the art as of like 2016, 2017. So, you know, by now for me to try to build a bibliography, I mean, it would be many, many pages. So I'm not going to try to do that. But I will point you in the direction of this book if you're interested in, you know, a deeper dive into the literature here. I would like to say, though, for participants of this seminar, it might be interesting to know that, you know, if this started off as a very theoretical way of thinking about invariant manifolds, it's become more and more computational, and it's found its way into more and more kind of applied problems. So I'll mention, for example, a number of papers by George Haller and his collaborators on really mechanics of solids type problems, beam sort of physics of beams and beam type dynamics, like a not a laser beam or something, or a beam of particles, but I mean a beam like a structural beam in a building or something. So they tend to refer to this, you know, you see titles like dimension reduction using spectral submanifolds, and when you dig into what they're doing, well, there's then citing these papers, these older papers on the parameterization method. And there's another group from France and Italy, French and Italian engineers, really mathematical engineers, doing similar kind of work in material science, where you see a lot of these parameterization method ideas really doing extremely sophisticated, to my mind, finite element type analysis in like nonlinear mechanics of solids. There's also another sort of very applied place where these ideas appear a lot, which is in celestial mechanics. And then I would mention Banu Kumar, Juan Gamino, Rodney Anderson, again, Rafael de la Llave, Andrew Jorba, Morang Zhu, and many others who, again, you could Google these names and celestial mechanics and parameterization, and you would start to see, you would get a sense of the literature on applications of these parameterization methods in celestial mechanics. Okay, and finally, I want to mention this a couple of papers by participants of the seminar, Emmanuel and Katie and Blake Barker and Chris have used some parameterization method computations in some tipping analysis of the carbon cycle models, which I might come back to if I have time closer to the end of the presentation. We'll see how far I actually get today. But okay, this is just to give you some sense of what's to come, of what the parameterization method is, and where it's, you know, where it's been useful. Okay. So now I want to sort of fill in some of the details of what, you know, I sort of suggested, well, it's this functional analytic tool for studying invariant manifolds. It's been used for maps and ODEs and delay differential equations and other things. So let me sort of show you some more explicit, let's write down some equations. And then after that, I'll really get into trying to, you know, solve some examples really like in detail by hand to really try to give you a sense of how you do this. So I think the easiest case we could think about is just to think about the dynamics generated by a diffeomorphism, call it F, some map from RD to RD. It could be a diffeomorphism just on some neighborhood, right? It doesn't have to be globally a diffeomorphism. But if you had some equilibrium and it was hyperbolic, you know, then even a smooth map would be locally a diffeomorphism. Okay, so let's just think about discrete time dynamics and say we have a fixed point. And we linearize at this fixed point, and we see that we have m stable eigenvalues. Okay, so we might like to study the m-dimensional local stable manifold attached to that fixed point. And to first order, that would be given by we could approximate with just the eigenspace. But to go to higher order approximations, the parameterization method would involve studying this functional equation. So we try to take okay, here lambda is the diagonal matrix of these m eigenvalues. So lambda is sort of the dynamics in parameter space, that models the stable dynamics in the full space. And we would like to conjugate that linear dynamics to the full dynamics, but only on the image of P. Okay, so here P is not a coordinate change on the whole space or something. It's only a map from a m-dimensional neighborhood or say some neighborhood in Rm into our full phase space. So if we had only one stable direction, you might think of this as a curve, but it could be a plane or higher dimensional space, but smaller than the full dimension of the phase space. Another idea could be that we look for a invariant circle for the same diffeomorphism. So in this case, we would maybe want a periodic map P and a maybe irrational rotation number omega. We would want that applying the dynamics to the image of this periodic curve was the same as applying the rotation in the curve, right? So this would be an equation for a parameterization of a invariant circle with rotation number omega. For ODEs, we could think about similar situations. So let's say we have now a vector field from RD, so a vector field on RD, maybe an equilibrium solution, P, this time instead of a fixed point. We have, again, maybe M stable eigenvalues at this fixed point, and we would like to study the attached stable manifold. Well, we can study this invariance equation. Here again, lambda is this matrix of eigenvalues. Now it appears as multiplication instead of composition. And this multiplication is sort of acted on by the derivative of P rather than composed with P. But otherwise, this is a very similar kind of equation. And if P solves this equation, then P is a parameterization of our local stable manifold. Now, for the moment, I'm asking you to take my word on claims like that. I'll try to show you in some other examples, why these are the right equations to be studying, right? Another situation we could be interested in is maybe we have a periodic orbit and we want to parameterize the stable or unstable manifold attached to the periodic orbit. Well, now we have a periodic variable sort of going around, and then we have a motion along this stable or unstable manifold, the sigma, and we'd like to find this parameterization of like a cylinder, which would be our, or an m-dimensional cylinder, which would be our local stable manifold, and that parameterization solves this kind of functional equation. Okay, an invariant torus. We could write down just like we talked about over here, the functional equation for an invariant circle. This is the functional equation for an invariant torus. So, you can see in all of these problems, you have some kind of linear operator involving P on one side of your equation, and then you have composition of your unknown parameterization with either your vector field or your diffeomorphism. So, I know this is throwing a lot of equations at people all at once, but that's the commonality I want you to see here in all of these parameterization methods. Somehow we're looking for an object that solves a functional equation involving our given dynamics and then some kind of linear operators that'll become more clear as I go on. Okay, so once you write down these equations, if you wanted to maybe do some numerics based on these, the short description of what you might do is you project these equations onto some Schauder basis, maybe Fourier basis, or some Taylor basis, or finite element, or whatever basis you're trying to work with numerically, and then you try to solve those projected equations. You might do that with some power matching argument or a Picard scheme or some Newton method. It depends. Okay, all of these ideas are sort of available to you. One way to think of this, if I was finding changes of coordinates from RD to RD that sort of simplified locally the dynamics, that's what normal form theory is all about. This is kind of like you're doing a subnormal form. I'm not trying to simplify the dynamics in a whole neighborhood of phase space, but sort of just on the invariant object I'm trying to study. So it's a sort of a simplified version of a normal form approach, and because it's simplified, in many cases it's easier to do than a normal form. Okay, and everything here I'm talking about are vector fields in RD or diffeomorphisms in RD, but of course if you had, for example, a partial differential equation, maybe you could think of like a nonlinear heat equation as a vector field defined on an appropriate Banach space, or at least on a dense subset of an appropriate Banach space. And you would be led to similar kinds of equations. Okay, so these ideas extend to fancier settings, but I wanted to maybe stick today with things that are closer to home. Okay, this is a high-level kind of overview. Let's get into some examples and try to see what we can do with this, and maybe if it's worth all of this why is this worth generalizing somehow? So one of the easiest, interesting dynamical systems that we've all worked with is this Henon map. It's a planar, it's a map of the plane, non-linear, but just barely. And we know this has interesting dynamics. It has a chaotic attractor, so it's just a classic example of a nonlinear planar discrete time dynamical system. Okay, one can check using like a Newton's method, or even for this system, you can work out by hand that this map has actually two fixed points. One of them is roughly given here. And by computing the derivative, you can see that this fixed point is a saddle. So it has one stable eigenvalue and one unstable. Okay, so this is a map. So the stable one is not the negative one, it's the one inside the unit circle. And this unstable one is the one outside the unit circle. It's sort of, the minus sign means we're flipping orientation here as we do the dynamics, rather than the stability, telling us the stability. Okay, this is a hyperbolic saddle. So what? So, well, we expect some stable and unstable manifolds attached to this fixed point. We can compute the eigenvectors, and we could look at, here's a simulation of the system with the attractor. Here's the fixed point kind of sitting in or very close to the attractor. And here are these stable in red and unstable in blue eigenvalues, plotted right at this fixed point. So if, to first order, these are the stable and unstable manifolds. And now what I'd like to do is compute higher order corrections using this parameterization method. So let's pick any fixed point. I'll just call it P now. And what we're going to try to do is solve this invariance equation, where lambda will be either our stable or unstable eigenvalue. We sort of have to pick. We have to decide which manifold we're going to look at. Okay, so we're looking for P, solving this equation. In fact, because F is analytic, I'll look for analytic parameterizations, although at first we're going to just proceed formally. One can justify all of this at the end, but the fact that if F is analytic and we have a hyperbolic fixed point, then we can find analytic parameter, expressions for the stable and unstable manifold. Okay, so I'm interested in analytic solutions of this problem. I want to normalize so that 0 is taken to the fixed point, and the derivative at 0 is my eigenvector. So in other words, I'm just imposing that P to first order at 0 is the linear approximation of the, say, stable or unstable manifold. Now, why is this a good equation to study, right? This is what I say I haven't really convinced you of yet. So in this easy case, let's think about this for a second. So the claim is that if we could find a solution of this equation, then we have actually found a parameterization of a local stable, unstable manifold for P attached to this, well, stable manifold attached to P and tangent to this eigenvector. So a P, I'm choosing, sorry, parameterization capital P, I'm choosing first, to fix these first order terms. Okay, to see this, let's just pretend it's true. Pretend we have a solution to the functional equation. And let's look at a point on the image. Okay, so we pick a sigma in -1, 1, and we look at P of sigma. That's going to be a point sitting up in the phase space, right? Well, now that we're in the phase space, we can apply the dynamics. So let's look at F of P of sigma. Well, now by the invariance equation, we know that's actually P of sigma applied to lambda. But since we're doing a stable eigenvalue, we know that lambda is less than 1. So if sigma was in the domain of P, then lambda sigma is still in the domain. And now we can do both sides of this equation again. So we can look at F of P. That's F of this P of lambda. But now we apply the invariance again, and we get the lambda squared, right? And inductively, we see that the kth iterate of a point on the image of P is the same as iterating lambda k times just in the parameter space. But we know lambda is less than 1, so we know what happens over here, right? So now as long as P is, say, even continuous, and we're really looking for a smooth solution, so we're looking for something continuous. As long as P is continuous, then the limit as k goes to infinity, I can take it inside. I know this limit, it goes to 0. I know that P of 0 is actually going to be my fixed point. So it means that orbits on the image of P really do accumulate to the fixed point. Okay, so a P solving this equation really is a parameterization of a local invariant manifold. Okay, this is just restating some of what I just said. So it's, that's why we care about this equation, okay? So once we've decided or convinced ourselves that we care about this equation, let's try to find the P. So the way I'm going to do kind of a formal series argument or computation. I'm going to make a power series ansatz, or I'm going to look for the power series of P. I'm introducing a little notation here because sometimes I might want to think about components when I start writing down these compositions. Okay, so here's my P of sigma. It's a power series, but I can write it in components like this, or even like this. Okay, well, if I take this power series and evaluate it at 0, I know I just get the constant term. So I want the constant term to match the fixed point that I'm trying to study. So that's the first thing we impose. Now, if we take the derivative of this power series, well, that just gives us this new power series. And if I evaluated this at 0, it's easy to see just by writing things out again that now I get P1, the first order coefficient. And so we want the first order coefficient to be the eigenvector. So this is kind of just what we already knew, right? We already knew that the fixed point and the eigenvector, that gives us a linear approximation. So this is just kind of how you impose it in the power series. And now what about higher order coefficients? So to see these, instead of continuing with this game of differentiating P, what we'll really do is we'll just take this power series and now we'll try to plug it into the functional equation. Okay, so if we take P and plug it into this functional equation, on the right, it's easy, right? If we take lambda and we just plug that in, we replace we replace sigma in our power series with sigma times lambda. That's this. And then the n distributes across both of these terms. And we just, in sort of coefficient space, this composition is a nice diagonal operator. We just get this lambda to the n in front of the coefficient P. Okay, which maybe I'll write like this if I'm thinking about components. On the other side, we have to take this power series and plug it into this map. So, here, I've started to write that out with the components. We can see we're going to have to square our power series in U. Okay, so that's an expression like this, where I've done the Cauchy, not the Cauchy product, excuse me, the yeah, the Cauchy product, exactly, the Cauchy product of power series. Okay, so the product of this power series in U, this U power series here with itself is just this expression here. And now we can kind of, each of these is an infinite series, so we bring the sum out front. The only term that doesn't look like a series is this 1 here, so I think of that as 1 plus 0 sigma plus 0 sigma squared and so on. So I have a really simple power series for this thing, and then everything can be written as a series. And now I have an expression like this, and two functions, two power series are equal only if the coefficients are equal. So we can match like powers here, and we get these equations for n greater than or equal to 0. Now we're only interested in the coefficients for n greater than or equal to 2. So for n greater than or equal to 2, things reduce to this, you know, that sigma n goes away, because that was only there at 0th order. And we have these still kind of nonlinear expressions for the u's. So we'd like to try to see if we could isolate terms of order n. So un and vn. Over here, the un and vn are sitting nicely. Over here, they're kind of still locked up inside this sum. So we look at this sum and we say, how could we get a term of order n here, you know, when we're doing one of these additions? Well, if k were equal to 0, we'd have un times u0. And if k were equal to n, we'd have actually u0 times un. So we get two terms like that. This is the only way that n minus k and k, the only way we could get an n there, well, those are the only two cases. And this is then everything that's left. Okay, so this is a sum involving only terms of order less than n. So we plug that back into our little homework problem up here, and we get this. And so now we can start trying to group anything of order n together. We get things like this on the right. So we have a linear dependence over here on terms of order n, and then this nonlinear dependence on lower order things. And this matrix here in this linear dependence, it's not just any old matrix. This is actually the derivative of f evaluated at our fixed point. The u0, v0, that's actually our fixed point we started with. So this matrix ends up actually being the derivative of our diffeomorphism, which is something kind of nice. And then we have these nonlinear terms and this thing involving the lambda, the products of lambda on the other side. So we'll isolate terms of order n on one side, and we get an equation like this. Yeah, that's for n greater than or equal to 2. So we already had the 0th term, the first order term. Now we have a sort of linear system of equations that define, you know, terms of any order as long as we have terms of the previous order. So we can find the P2 using that we know P0 and P1. And then once we have P2, we can compute P3 and so on. Okay. All right. So let's kind of store this over here. All right, so these are sometimes called the homological equations for this parameterization P. So like the recursion equations for these Taylor coefficients. Okay, so what we just did was especially worth doing, I think, because it's indicative of what has to happen, what always happens, which is that these homological equations always look like your derivative of your diffeomorphism at your equilibrium. Now, for a one-dimensional manifold, this will always be your stable or unstable eigenvalue to the nth power times your nth coefficient, and then some nonlinear term that depends on lower order things. Where this Rn, you really have to work out, you know, it really depends on the form of your map. But every time you do one of these problems, when you think you've arrived at the correct equations, you have a great check, because your left-hand side should always be the derivative, you know, minus this lambda times the identity. Okay. Another nice thing to see, at least in this case of a one-dimensional manifold, is this matrix is always going to be invertible, because this is a characteristic matrix for the linearization. at P0. This is invertible as long as the number sitting right here is not an eigenvalue. And so, suppose we only had one unstable eigenvalue. When we start taking powers of that, it only gets bigger. It can never hit one of the stable eigenvalues. So this lambda to the n is never in the spectrum, at least in this one-dimensional case, or similarly for the stable. So these PNs are formally well-defined to all orders. And okay, this is, of course, the question of convergence, but we're not going to worry about that too much today. So here is a picture. Let's see, what did I do here? I did the stable manifold, which is the blue one, I think to 20th order with an eigenvector scaled to length 1. And then I tried to compute a little more for the red one because it's a little more interesting. I went to order 20 and to eigenvalue scaled to length 4. And, you can really see you're getting not just a local picture of this red unstable manifold of the fixed point using this method. We're really seeing, for example, this is not a graph over the eigenspace or something. It comes over here and turns around. It comes over here and turns around less aggressively. And already just in this local picture where, again, I'm just plotting these polynomials, I'm not iterating these local manifolds yet. You see an intersection between the stable and unstable manifold. So you have this suggestion of a horseshoe already just by computing these local manifolds and plotting their images. Okay, so this is an example in the Henon map, and I think here you can really see all the steps in kind of gory detail, right? Okay. Yeah, I think I said most of these things. This calculation, this would be a classic kind of parameterization-y method calculation, but this calculation that I just showed actually appeared in the literature before the term, 20 years before the term parameterization method was ever coined. This idea of solving a conjugacy equation with formal series is very natural in dynamical systems theory. So I just want to make that clear, right? That a lot of these ideas have been around for much longer than long before these papers of Cabrifonte and Delle Ave. Okay. Now, that was kind of the easiest example I could think of. We had a quadratic nonlinearity of a planar map. If we started looking at dynamical systems we were interested in for 5 minutes, we would come up with much more complicated models. So, can you do these things in more complicated systems? So what if you had, instead of a polynomial, it's easy to imagine if I have polynomial nonlinearities, I can always do these kind of Cauchy products to work out how Taylor series or how power series multiply. Polynomial multiplication of power series is kind of easy. But what if I had a map like this where I had some non-polynomial nonlinearity? Okay, so if I was looking at a fixed point of this sort of Leslie type population model, I've taken kind of a Henon map and just given it this exponential nonlinearity. So if we were at a fixed point, the parameterization invariance equation would look like this. And now we would have to take a Taylor series for u and v and plug them into this exponential and try to work things out here. So this would be a lot more complicated. But there's a nice trick that really simplifies a calculation like this, which is you can introduce a new variable, which is this sort of transcendental nonlinearity, and then you can use the fact that most of the nonlinear functions that we use in mathematics or mathematical physics, they mostly solve, they typically are solutions of some differential equation of their own. So once we write down that w is going to be this e to the minus alpha u plus v, then we can differentiate w and apply the chain rule. We see that we get this expression. But now this e, this exponential term out here, is just w again. Okay, so we really have that w solves this differential equation right here. And so if we append that to our invariance equations, then we're sort of back in the setting of polynomial nonlinearities, right? We just have to deal with Cauchy products here, even though we do have derivatives. But derivatives of power series are also straightforward, and one can work out the coefficients for u, v, and w here. It's not much harder than the problem I just did. Okay, so the polynomialness, or the polynomial, the vector fields are polynomial is in the end not so important. Okay, and different people refer to this technique. I learned this technique out of Donald Knuth's book, Art of Computer Programming. There's a chapter on what he calls semi-numerical algorithms, and there's a lot of talk about working with power series. But some communities call this polynomial embedding, or others call it quadratic recast or polynomial recast, or automatic differentiation for power series. This has lots of names. Okay, but it's an idea that goes back, really hundreds of years even. Another generalization of what I just showed you is you could say, okay, fixed points are great, but the Henon map has period 2 points and period 10 and 15, 20 points. What if I want to study the manifold attached to a periodic point of higher order? Well, of course, you could just look at compositions of the map. So, a periodic point for F, a period 2 point, for example, is a fixed point of the composition map. The problem with this computationally, theoretically, this is the right way to think about things, but computationally, this takes a nonlinear problem and composes it with itself. You get a much more challenging nonlinearity. If you were just doing the Henon map and you composed it with itself once, you'd go from a quadratic to a quartic nonlinearity. So, computationally, this might not be the best thing to work with. Typically when you compute periodic orbits, you do it by some kind of multiple shooting scheme that lets you only look at, the application of the map and not its compositions. You sort of unfold the compositions. Could you do that for these manifolds? Could you somehow do some multiple shooting that unfolds the compositions? And you can. So my former PhD student, Jorge Gonzalez, looked at, this was one of the several really fantastic things he looked at in his PhD dissertation. But so the idea is you could try to parameterize at the same time the manifolds attached to, say, P1 and P2. And so you would have an arc parameterized by P and an arc parameterized by Q. And those P and Q solve a system of functional equations, so that F of P should put you on Q, but if you're using sigmas to parameterize both arcs, then you should now have moved by this linear term. And likewise for F of Q, right? I hope people aren't, there's a lot of thunder and such outside my window, so I hope it doesn't interrupt the internet, and I hope it doesn't interrupt the sound too much. But anyway, keep going. So here these would be the sort of first order constraints, right? So we would need to impose or normalize P and Q at 0 to take us to the period 2 point. And then the tau here is actually not the sort of what you would call the multiplier for the periodic orbit. The eigenvalue associated with the linearization of this map, it's actually the square root of this, or the nth root if we were doing period n orbits. But once you write down these equations, you can simultaneously solve them using like power matching ideas, like I did before, and you only have to deal with F and not compositions of F. So like the nonlinearity is no harder for this system than it was before. It's just the dimension of the problem goes up. And if you're solving linear systems of equations, you're not so worried about the dimension going up from say 8 to 20 or 20 to 80 or something like this. This is no problem at all. But those compositions of more and more complicated functions really could be kind of problematic. Okay, let me kind of skip over this comment here. But if someone was interested in looking at more of this, here's this paper where Jorge and I wrote this up a few years ago. And here's a nice picture from that paper where we looked at sort of all the periodic orbits we could find on the Henon attractor up to, I think, period 16. And there are many, say, period 5s and many period 7s and many period 9s and, in some cases, 8, 10 different orbits of the same period. And then for each of those periodic orbits, we parameterize just the polynomial parameterization, no extra iterations, no extra globalization. We parameterize the attached stable and unstable manifolds, and then we just plot those, the images of those polynomials. And by doing that, you get a really good sense of what the dynamics are near this attractor. So the unstable manifold is always kind of stretching along the attractor. The stable manifolds are always bringing you into the attractor. And this is a classic, but a pretty rich picture of what's happening near the attractor. Again, just by parameterizing these local manifolds for a bunch of periodic orbits. Okay, I want to change gears a little bit and talk about some differential equations. So, I'll use as an example the Lorentz equations that everybody's familiar with, and we'll think about it now an equilibrium solution. Okay, so in this case, let's say we have an equilibrium P, and we have just say a stable eigenvalue in its eigenvector, and we want to now parameterize the stable or unstable manifold attached to that equilibrium. Sorry, it's getting a little distracting outside as the weather is pretty intense. I'm going to go a little fast here, I think, because I did kind of a lot of detail on the xenon example, and time is moving on now. But the invariance equation for this 1D manifold is going to be this. So now I want to solve this equation for P. I have a little, quick calculation of why this is the right thing to study. Again, I'll go through it really quickly. Suppose you solve this. I want to convince you that the image of P is a stable manifold for this equilibrium solution. Well, so what do? I look at a point on the image of P, and then I define a curve, which is that I apply this exponential dynamics in the parameter space for this map P. Okay, so now what I want to do is show that this curve, which is basically parameterizing the image of P, that this is a solution curve for the differential equation. So this is an invariant curve. Well, you do that just by differentiating, then applying the invariance, and then applying so to get from here to here, we use the invariance. And so then this is basically saying that gamma prime, well, it's this expression, but this is gamma, right? So we do have that gamma here is a solution curve if we've solved this, this differential equation. Okay, so this is a good thing to do again, right? If we're interested in these stable and unstable manifolds of equilibrium. So now we can play exactly the same game. We make this power series ansatz. We plug the power series into this invariance equation, and exactly the same kinds of things happen as before, and we end up with linear equations recursively defining the coefficients of our parameterization. This time, instead of a lambda to the n, we have an n times lambda, but otherwise we have very similar equations for these manifolds for the ODEs instead of the maps. Okay, so everything here is completely explicit, and it isn't hard to write a computer program that solves these equations and maybe plots the results. So here's an example of that in Lorentz for 1D manifolds of each of the equilibria, and I've picked a set of parameters here to do this at, so that if you extend the manifolds, so the black curves here are obtained by integrating the manifolds a little bit, and at this carefully chosen parameter value, these 1D manifolds actually intersect and tie into this nice little torus knot, the trefoil knot, excuse me. So it's just it's a cute picture that shows you some nice 1D manifolds in Lorentz. At a 2D manifold, so say you have a pair of, say, stable or a pair of unstable eigenvalues, your invariance equation is now this. How do you see that? Well, this time I'm going to do even less, but if someone wanted to work this out, you can just pick a point on the image of P and then apply these linear dynamics to define a curve on the image of P, and you can just check that that curve is a solution, so that the image of P really is invariant under the dynamics generated by F. And then it's, you know, exactly the same kind of formal series calculations to get to the coefficients of this now two-dimensional manifold. And they look very similar to before. Now we have these more complicated combinations of the eigenvalues, and we have to worry a little bit more about, can such a combination of the eigenvalues ever be an eigenvalue? But as long as the answer is no, then we can solve these to all orders once again. So here's a couple of pictures of the 2D manifolds at the eyes, and the local the local 2D manifold at the origin in the Lorentz system. And this picture's taken from a paper that Maxime Burdin and John Philippe and I wrote a number of years ago. Okay, the last thing I could mention really quickly is this parameterization now for, say, the stable or unstable manifold attached to a periodic orbit. And I wanted to explain this in a slightly different way. I wanted to give more of a geometric picture of what's happening here with this parameterization method, rather than such an analytic sort of discussion. And I think with the manifold of a periodic orbit, the geometry is interesting enough to make it an interesting conversation. Okay, so let me maybe just try to finish up with these couple of slides about these periodic orbits. So let's say you have a periodic orbit and you have say a single stable flow K multiplier for this periodic orbit. So you know you have a tube attached to this periodic orbit, a tube consisting of orbits that accumulate to your periodic orbit. In other words, this thing has a stable manifold. Okay, and then here's a depiction of what that manifold might look like in phase space. Well, you can build a model of just the dynamics on this tube. That model is just a cylinder where we have really simple dynamics on this cylinder. The dynamics are to go around the circle, we just flow with unit time. So we're just going around and around and around. If we're at sigma equals 0, there's nothing here in the second component, so we just go around the equator forever. That's our model of our periodic orbit. And if we're off, if we have some height on this cylinder, then we have this vector field pushing us down to the orbit. Okay, so this is like a vector field that models the dynamics on a stable manifold for a periodic orbit. So what we're looking for is a parameterization that embeds this model in our actual system, right? And you know, we want the dynamics in our model to be the same as the dynamics on the image of P. Okay, so again, we have a very explicit vector field for our toy dynamics on the cylinder here. And we're looking for this map P. Now, what we know about the derivative of P is that it's an object that can take vector fields defined in the parameter space and move those vector fields to the image of P. And the way you do that is you multiply the vector field defined in your toy space, you multiply it by the derivative, right? This is just the push forward of a vector field by P. Well, the columns of this derivative are just these partial derivatives. And so if you multiply things out, what do you get over here? You get this nice linear partial differential operator. Okay, so this is how P takes the vector field defined on our model space and takes it over here into Rn. Well, I want orbits over here to match orbits over here. So what I want is that the vector field on the image of P that I get by restricting my dynamics in the full phase space to be the same as the vector field that I get when I push forward K by P. Okay, and that's just this equation. So this is, you know, exactly the same kind of functional equation. I think I stated this in the second or third slide, exactly this equation. But you can see this is another way to see where these kinds of equations are coming from. You know, they have a nice geometric interpretation in addition to all of this analysis, right? So this is like an infinitesimal conjugacy taking this toy model into our true system. So again, that gives more of an intuitive explanation of why solving an equation like this is finding for us these parameterization of these invariant manifolds, where we're not just parameterizing the manifold, but where we know the dynamics. We understand the dynamics on both sides of the picture as well. Okay, so for the case of a periodic orbit, this P, we want it to be some kind of maybe periodic in theta, and then sigma is height on the cylinder. At 0 height, we want to have the periodic orbit, and then, you know, we should be tangent to the not eigenspace, but sort of the eigenbundle or the stable bundle attached to this periodic orbit. That's what P should do at first order. And again, you could try to solve this equation to do higher order corrections. If you actually do that, say in Lorentz, you compute some periodic orbits and try to solve this in now, say, Fourier-Taylor space. So you look for a Taylor series whose coefficients are Fourier series, and you plug this ansatz into your invariance equation again. You know, you're led to equations that look a lot like what we had before, these homological equations. Now, instead of being linear algebraic equations, it's a linear differential equation for each one of these Taylor series coefficients. And again, it's linear for the nth order term, but we need to know the lower order terms, and our equation depends in a nonlinear way on the lower order terms that we already computed. Okay, and if you discretize again with like a Fourier-Taylor series, then you can do all of this in coefficient space. Maybe not now with power matching, but maybe with some Newton method. Okay, and here are a number of papers that talk about these kinds of numerics, and here's an example of a nice stable manifold attached to one of these short periodic orbits in the classic parameter values of the Lorentz system. I think my time is up. So I had some more, maybe something a little more applied, talking about this carbon cycle model. But in terms of a nice introduction to the parameterization method, I think I've kind of covered the things I wanted to say. And I think this is a good place to go ahead and stop. So, you know, let me jump ahead here to this, and just thank Emmanuel for the invitation, and to thank everybody, either who's here in person while I'm talking, or anybody who might have watched this or be watching this later online. Thanks a lot.
Yeah, thank you very much, Jay. Yeah, it was a great talk. Send a clapping emoji, of course. Yeah, so I think we probably have a little bit of time for questions if anybody has one. Chris, yeah, please.
So, I mean, as I understand, the basic strategy is always to, you know, use this sophisticated method to find a local invariant manifold. And if you want a global manifold, you push forward in time or backward in time, or iterate forward in time or backward in time. But that also has a certain error in it, which is always estimated by the derivative of the vector field, I guess. I mean, can you balance those things out by finding a larger sort of domain on which you get the power series to converge, or is that?
Yeah, so it's nice to get far away from the equilibria, you know, where things are acting linear before you start integrating, right? But as you say, eventually you have to start doing some kind of numerical integration, and you might do a high order Taylor integrator. For a lot of these kind of analytic systems is a very accurate way to integrate these systems. And then, as you say, you can keep track of your errors. Of course, they grow. The longer you integrate, the more error you have. But if you're looking for connecting orbits, then you don't really need to integrate forward in time the whole manifold. I mean, you might do that numerically to sort of locate an approximate connection. But once you have approximate connections, you can start solving boundary value problems that start on one manifold and end on the other. And then you're doing iterative schemes that, again, have great or good error improving properties, right? So if I take a point on the unstable manifold and integrate it 10 time units, I might get a much worse error estimate than if I start on the unstable manifold, do a 2-point boundary value problem to the stable manifold and then do Newton on that, even if it's also 10 time units, my errors can be much, much better. So, you know, for connecting orbits, which are often things that we're interested in, you can hope for much better errors than just picking some point on the boundary of this manifold and integrating for a long time. Okay. Although that can be done too, and we've put some effort into that as well. Shane Kipley especially wrote several papers where he was cutting the boundaries of these manifolds up into pieces and propagating those pieces in a really careful way. And you know, this is also something I'm interested in, but of course, there's only so long you can do that. The errors will eventually catch up with you.
All right. Let me follow up Chris's question by asking whether you've explored using analytic continuation in problems that are analytic as an alternative to integrating the systems.
Okay, so at first I thought you meant, so we've done a number of things in this. So I mean, in some sense, yeah, I mean, anything you do that takes the boundary of the manifold and propagates it, I would call that integrating. I mean, you know, you could set it up as an analytic continuation problem, or you could set it up as a Picard fixed point, or whatever you want to do. But you know, if I'm solving initial value problems, that I would call that integrating. And you can correct me if I'm missing some subtlety of your question. But another thing that we've done is once you have a connecting orbit, or once you have one of these manifolds at one parameter value, you could try to do continuation of, say, a connecting orbit or a periodic orbit, or these manifolds themselves to other parameter values. And then you can try to do expansions again in the parameters, and we've done some work in this direction as well.
Yeah.
So
and yet one more question in this vein is, have you looked at rational function approximation for the series that you compute as an alternative to Taylor series?
We've looked at some rational function approximations. You know, there are these methods that can be really useful for trying to numerically locate where poles might be, right?
Yeah.
And we have definitely played around with some of that numerically. It's hard to turn these things into, like, okay, I didn't talk at all about computer-assisted proofs, but that's often something we're interested in. But so one thing you can do is you can try to locate poles using this rational approximation that you're talking about. And then you could try to prove that they're there by doing more classical analytic continuation, like really continuing into the complex plane and trying to do some monodromy, where you go around a pole that you didn't know where it was until you guessed with some rational approximation. That's as much as I've done in that kind of direction. But we've certainly used lots of bases, like not just Taylor, but Fourier, Chebyshev, even finite element approximations to do these kind of computations.
Thanks.
My pleasure. Thanks, John.
Okay. Any other questions for Jay? Okay. If not, then yes, let's thank Jay again. It was a very interesting talk. I really appreciated the geometric argument at the end. That helped me a lot. So
yeah, great.
Okay. Yep. Then if no other questions, I think we do not have a talk next week, but we probably pick back up the week after, I think. I'm not wrong. So, but I'll send emails, of course. Well, thanks, everyone.